Today we'll be going through Morpheus and how you can utilize AOM's data processing tool to help process your hologram measurements quickly, easily, and accurately. First step when you open Morpheus is to load the CGH file. This can be done by selecting the Load button in the top left corner. If you have contacted AOM, they will have sent you a CGH file for your computer-generated hologram. This file is effectively a digital representation of the hologram. When we first load the file, we'll notice the pattern itself on this left-hand side. This gives you a quick method to check that you are utilizing the right CGH file for your hologram, as the pattern and numbering should match your hologram that you tested your optic with. The next thing that we'll notice is the transmitted wavefront error map in this primary area. As we can see, the transmitted wavefront error map is the transmitted wavefront error, or TWE, of the substrate of the hologram itself. The figure error is very small, as we expect. Additionally, we notice that the fiducials are marked. There are, on a standard hologram, 5 fiducials to be marked. These are marked when AOM first produces your CGH, and the TWE map is also measured at the same time. If you would like, you can always load your own TWE map by selecting the load file here. The next step is to load your measurement data of your test optic. To do this, we click the load button. We will select our measurement file. The measurement file currently can be a DAT-X or DAT file. We'll click load, and this will load our measurement of our test optic. As we can see, we've not done any masking of the optic. The only thing that is required when you load your data in is that you've marked your 5 fiducials in your measurement. This can be done using the MX software or whatever interferometer software you utilize. Please refer to your user manual in order to learn how to mark these fiducials. Additionally, you must have not removed tip and tilt or any higher order terms from your measurement, because due to the distortion that can be present, these terms may not perfectly represent tip and tilt. We will remove these after we have done distortion correction. The final step is to simply click Run. Once we click Run, we can see that Morpheus is working on processing your data. You can see the current status of what Morpheus is doing in the bottom left-hand corner. The first step in the processing is to remove substrate error. We can click the eyeball mark to see the results. In the top left corner, we see the initial surface error. In the bottom left corner, we see the TWE map aligned now to our measurement. And in the right panel, we see the test optic surface error after the TWE has been removed. We can note that the overall height has not changed very much because the TWE is so small. Additionally, we see the residual fit error here on the top bar. The residual fit on the top is in units of pixels RMS. If we zoom in, we can notice that there is not a perfect overlap of our marked fiducial in the TWE map and the marked fiducial in our measurement. Of course, these will almost never be exactly the same. There will be some residual difference. That being said, if the residual difference is small, less than typically 1% of our overall pixels in the measurement map, then it's not a big issue. Morpheus will alert you if this number is too large, and if it is too large, then we recommend that you go back to your measurement and remark the fiducials. The next step in Morpheus is to then look at the mapping correction. We can click the eyeball next to mapping correction. In this state, Morpheus will take the mapping between the test optic and the CGH and remove any distortion that's present in that process. This distortion simply happens due to the geometry of the test. By taking a uniform grid of points on the test optic, we can map where they hit on the CGH. We can then identify the mapping relations between the two and apply this to our measurement to remove any distortion. We can note now in our measurement that it is a rectangular surface measurement. if we compare this to the initial input measurement data, we note that originally it was slightly compressed in one dimension and slightly expanded in another dimension. Additionally, this has now set our x here and y here axes to be correctly defined. Now x and now y. The last thing to notice at this stage is that the tilt and tip in x and y has been removed. The final stage of Morpheus is to look at the misalignment, fit, and removal. Morpheus will identify the misalignments, including x and y decenter, clocking, if applicable, and spacing between the test optic and the CGH. I do want to note that not all test geometries have every single one of these 4 misalignments as applicable. For example, for an axisymmetric optic, clocking would be a degenerate mode, or for a cylinder optic, X or Y decenter might be a degenerate mode. That being said, for this optic, which is a full freeform, these are all valid modes. The first thing to notice is in the top left corner. This is our initial mapping distortion corrected data. Below this, we see the total alignment errors removed. We will explain what goes into this in one moment. On the right-hand side is the final measurement with all alignment errors removed. We can notice that there's been a significant reduction in surface RMS, indicating that for this test, the primary amount of surface figure error was actually from a misalignment of the test geometry. How do we fit these misalignment errors to our data in Morpheus? As we stated in the beginning, the CGH file is a digital representation of the CGH test. When we create a CGH at AOM, we take the model of the test geometry and we define certain perturbations in terms of decentered clocking spacing, and we then record the sensitivity and the precise mode of what the surface figure error looks like from that misalignment. In Morpheus, we then we use those maps, which are in the CGH file, and we fit each misalignment mode to your measurement data. Because it's fitting the full misalignment mode, this is a very specific method to identify the misalignment error. This is not utilizing other methods to fit the error. Thus, in general, this method is highly specific and highly accurate. We can notice at the misalignment modes below that for each mode, there's a small map showing the exact figure error that arises from that misalignment geometry. Each of these maps are what are fit to our data. Additionally, we can notice the alignment sensitivity. This is in units of microns RMS surface figure error per whatever unit our misalignment is. In terms of decenter, this is per millimeter. In terms of clocking, this is per degree. Below this, we see the alignment error from fit. This is the exact amount of misalignment error that was detected. Thus, we can see for X decenter, there's 4.235 microns of decenter of our test optic to our CGH along the x-axis of our test optic. There's 135 microns of decenter along the y-axis. There's only negative 0.006 degrees of clocking, and then there's 145 microns of spacing. Thus, the dominant misalignment modes in this test were actually spacing and y decenter. This information can in fact be utilized to do an immediate in situ adjustment of your test. If you can precisely adjust your motion by this amount, then you will be able to perfectly align your test optic to the CGH. Perhaps most importantly is the induced surface figure error from the misalignment. This is in units of microns RMS surface figure error. Thus, the total contribution from the X decenter induced 0.018 microns RMS surface figure error. However, Y decenter we notice induced 0.432 microns RMS, and Z spacing induced 0.690 microns RMS. Once again, as we expected, the most dominant misalignments detected contributed the most surface figure error. Lastly, we notice the global tilt error in the measurement data and the tilt error from alignment fit. The global tilt error tells us the total amount of global tilt that is detected in our measurement. For each of these misalignment modes, they are tip and tilt compensated. That is, we define the modes as if you were utilizing the interferometer in real life and were using tip and tilt to, in effect, minimize the fringes. Thus, this is X decenter compensated with tip and tilt, Y decenter compensated with tip and tilt, clocking, spacing, etc. compensated with tip and tilt. So, in the prior step, we noticed that we removed tip and tilt from our measurement. That value is recorded, and we also notice that there is some tip and tilt present in each of these maps. If we sum the total tip and tilt in the maps, here the misalignment modes, and add that to the tip and tilt removed, this gives us our global tilt error in the measured data, which again can be useful to go back if you're performing an in situ measurement and adjust to achieve precise alignment. In the misalignment error and alignment removal tab, we can also select which modes we want to fit. Perhaps we do not want to fit all of the misalignment modes. In this case, we only wanted to fit X decenter and Z spacing. We can simply click this bar down here to select which modes we want to fit. Additionally, we can simply fit them and not remove them. In this case, we can see how much of each misalignment mode is present, what its contribution is, but we notice that the alignment errors removed is a map of zeros. That is, nothing is removed. We get the original data. This can be useful if you just want to observe this data and not actually remove any terms from your measurement map. For our case, we will fit and remove. And at this point, we're now done with the Morpheus processing. We can click export, and this will let us save our data map to the original input data file format. One additional step, if it's of interest to you, is the uncertainty analysis. On this page, we see all the information from our CGH file. The CGH file records the total test uncertainty as manufactured, as measured by AOM, coming from the hologram. This includes design residual error, encoding residual error, patterning error as built, etc. These values are recorded and measured by AOM when we make your hologram. As you can see, the basic CGH test uncertainty, RSS value, is extremely small for this test case, 1.57 nanometers RMS. Going over to the top right, we can see the alignment contribution to test uncertainty. In this table, you as the user need to input the values for your test uncertainty. When we design the hologram, we record the sensitivity of each of these misalignment modes and how it contributes to the total test uncertainty. You need to input the actual values for your alignment tolerance. For example, if the UUT X decenter tolerance was something very loose, 1 millimeter, for example, you would input 1 millimeter, here's the units, and this would update the total surface figure error on the right. All of these then get stacked in an RSS calculation to provide you with a total surface figure error alignment uncertainty from the test geometry. The last number that you as a user need to input is the test optic measurement noise. This is simply the measurement noise that you anticipate from your interferometric measurements. Of course, this can always be reduced by increasing averaging and other methods. Let's say that it was 5 for this test. We now have the UUT data uncertainty value here. All of these uncertainty values then get stacked in an RSS calculation to provide you with the total test uncertainty RSS. In this case, 5.465 nanometers RSS. This represents the total uncertainty in your measurement from the contributions listed above. This can be useful in a report to detail how the measurement went. This concludes utilizing Morpheus